Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry, made easy. In this video, we'll be looking at using IUPAC rules of naming for looking at benzene and substituted benzene. So that's where benzene has different groups attached to it. Before we actually look exactly at how to name benzene molecules, we just want to see how they fit in the wider scheme of organic chemistry. So all of organic chemistry is based around the carbon atom, and usually that forms a lot of bonds with hydrogen. So we've got hydrocarbons at the top, and then we can split hydrocarbons into two different camps. We can call them either aliphatic or aromatic. Now technically, aromatic basically means a cyclic or ring-shaped, flat or planar structure with resonance bonds. And this idea of resonance pi bonds are pi systems, so p orbitals next to each other. So here we have two pi bonds, which are adjacent to one another. This pi bond is made up of two p orbitals. This pi bond is also made up of two p orbitals. And to create that pi bond, what happens is that these orbitals overlap. And this overlap looks like this. And so you end up with one pi bond here. Remember, these aren't separate pi bonds. Collectively above and below the carbon chain, that is a pi bond. And we also get this pi bond here. Now, the reason we can't just have cyclic, planar, and pi bonds, and we'll look at an example in aliphatic in a minute that is an exception to aromatic, is because they are resonance. And what we mean by that is you can see these pi bonds are literally next door to each other. So the pi bond here and the pi bond here, in three-dimensional space, can interact with one another. So you get these overlapping with one another even more. And you can see this overlap here, and we call this a conjugated pi system, and also known as allowing resonance. So that's what this term comes from. So resonance pi bonds and conjugated pi system pretty much mean the same thing. It only happens when you have a double bond spaced by a single bond spaced by a double bond. Here you can see this is a straight chain, so it's not cyclic. So this isn't an example of an aromatic, it's just demonstrating resonance pi bonds. But if we take cyclic, planar, and resonance pi bonds all together, then we get benzene. Now, at A level, this is the only aromatic you're going to be looking at. Benzene here, first of all, you can see it's cyclic. We've got 6 carbon atoms. It's also planar, so if we were to view this at an angle, so imagine I was viewing this benzene ring side on, and if we just number these, you can see that we've got this all happening on the same plane. And then finally, we need to show that we've got these resonance or conjugated pi bonds. So remember in our previous example, we had a double bond, single bond, double bond. So if we start here at 1 to 2, make that a double bond, 2 to 3 single bond, 3 to 4 double bond, 4 to 5 single bond, and then 5 to 6 double bond. So it has to be alternating between double, single, double, single, double, single. Any other variation wouldn't work. And then this gives us benzene. Just a note here, for benzene, the bond angle around each of the carbons in the ring is 120 degrees. So if I just draw the hydrogens in now, there's our first two. I'm going to draw the others in. So because they're on the same plane, we can see that around each carbon, there's 3 areas of electron density. So the angle is going to be 120 degrees. And then this is also the shape around that carbon, therefore is trigonal planar. If you're unsure about how we came up with that shape of the molecule around the carbon atom, then be sure to watch the video Shapes of Molecule on the YouTube channel. There are other examples of aromatic compounds out there that do not include benzene in, but do include these 3 different things. But at A level, you don't need to know about that. So at A level, as long as you can identify a 6-membered ring where it's got this conjugated system of pi bonds, then we're all good. Now, aromatic and benzene chemistry is new for year 2. What you've been focusing on in year 1 is aliphatic chemistry. Now, aliphatic can basically be seen as anything that doesn't contain aromatic compounds. And within aliphatic, hydrocarbons, we can class them in different ways. We can call them linear or straight chain. We can call them cyclic, and cyclic contain ring structures, a bit like benzene, but without the resonance pi bonds. And we can also class linear and cyclic as either saturated or unsaturated. And saturated does not contain carbon-carbon double bonds, and unsaturated does contain carbon-carbon double bonds. And so this just gives you an overview of organic chemistry. For example, if we drew a ring structure, so a 6-membered ring, and that was cyclohexene, then this would actually fall in the category of aliphatic, because whilst it is cyclic and aromatic are cyclic, it's quite obvious that it does not contain the pi bond network that we see here, because there's only one pi bond. And even if we introduced a second pi bond here, it still wouldn't allow for that conjugation. And even if we put a second pi bond here, and if we just draw that, then that doesn't go around the whole ring system like benzene does. So going back to the cyclohexene, because there's only one double bond in there, it also is not planar. Now, whilst on a 2D image it looks like this could be in the plane of our screen, due to each of these carbons here, 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 and here being tetrahedral, and you can see that by me just adding in the hydrogens at these positions, and also I'm going to add the hydrogens in at positions 5 and 6, so you can see the difference. You can see here in 1, 2, 3, and 4, we have 4 areas of electron density around this carbon in the middle. So that's tetrahedral with bond angles of 109.5. Then looking at positions 5 and 6, these only have 3 areas of electron density. Remember, the double bond is still just one area of electron density. So we've got 1, 2, 3 around this carbon, carbon 6, and that's the same for carbon 5. Then that is going to be trigonal planar, just like any C double bond C carbon, and that has a bond angle of 120. So between carbons 5 and 6, they are flat because they're both trigonal planar, but carbons 1, 2, 3, and 4, because they're tetrahedral 109.5, they are not flat at all, and so we don't have that planar cyclic network. So you can see here, this is why we allocate it as aliphatic. It's unsaturated because it's got a carbon-carbon double bond, and it's cyclic. It can't fill the criteria to be aromatic or a benzene. So here's our stripped back version of organic chemistry and the key terms, etc. So we're going to now focus in on how we name aromatic benzene containing molecules. When naming aromatic compounds, we're looking for the benzene pattern. So this ring can either be displayed as this or this. Now, where benzene is present, benzene can either be determined as the main functional group, or it can be determined as not being the main functional group. If benzene is the main functional group, then benzene is used as a suffix, so at the end of a name. An example of this is methylbenzene, also known as toluene, or nitrobenzene. And you can see in each of these cases, benzene is at the end of the molecule. Another example is where halogens are involved, and so, for example, if we had chlorine attached to the benzene, we would get chlorobenzene. Now, where benzene is not the main functional group, instead of benzene, we use the word phenyl, and this actually goes before the stem of the hydrocarbon's name, and so it's used as a prefix. There are many functional groups that are priority over benzene, so go via this route. These include amine groups. So here we have phenylamine or phenylamine, and we can see that we're using a prefix. Ketones are also high priority. An example is phenylethanone, with the F part of this being from the 2 carbons involved in the ketone. Now, where benzene has an OH directly attached to it, this is called a phenol. So it borrows the phen bit from phenyl, and ol for the fact that it's got a hydroxyl OH on it. So we can see the ol there for these two OH groups, and the phen section of this is all due to the benzene ring. A word of warning, the benzene needs to be directly attached to this OH group. So you can see here the carbon of the benzene is directly attached. So this example here is not an example of a phenol because the OH is one carbon away from the actual benzene. So this gives an overview of how to name the different benzene-based functional groups. But what's important is if we have more than one substituent. So what if we take this phenol, for example, and add on a chlorine to one of these positions around the ring? How would we go about naming that? So with polysubstituted aromatic compounds, where we've got more than one substituent around the ring, then what we need to do is to number these substituents. Now, one of these substituents is going to be designated as position 1. Now, in order to make the decision of which of these substituents is position 1, it's first worth noting that in this example here, it didn't matter which one of these we would number as position 1 because the substituents are exactly the same. They're both methyl groups. So if I wanted to, I could label this as 1 and this one as 3. If an OH group is directly attached to the benzene ring, making it a phenol, then this automatically gets given the priority of position 1. And then for any other substituents that are found on this phenol is going to be numbered relative to this carbon OH position being number 1. Now, if OH isn't present, so it's not a phenol, then instead you need to look at the substituent group and look at the atom that is directly attached to the ring and look for the one with the highest relative atomic mass. So take, for example, this one. So here in this example we have a chlorine and a carbon on the bottom that is directly attached to the ring. Now, chlorine has an atomic mass of 35.5 roughly, whereas carbon has a relative atomic mass of 12. So it's evident that the highest relative atomic mass is chlorine, so we're going to designate it this position here as number 1, and then relative to that we have position 2, 3 and 4 for the position that's directly attached to the carbon of the CH3 methyl group. Now we also want the combination of numbers to be the lowest possible arrangement. So if we look at this example here where we've got dimethyl benzene, I could label it as one of these positions where the substituent's attached as 1. So let's just choose this one. And then relative to that, I could go all the way around 2, 3, 4, 5. So this would be called 1,5-dimethyl benzene. Now, most people will be able to see that there is another arrangement that will give us a lower set of numbers. So 1 and 5 is quite high. If we instead labelled this as 1, this is 2, and this is 3, that would give us a lower overall set of numbers. And so, given this, we're going to choose this one and reject this arrangement. The final thing to take into consideration is if you have different substituents, the final thing to take into consideration is that if you have 2 or more different substituents, then you need to list them in alphabetical order, irregardless of whether this alphabetical order will give you a set of numbers that go from high to low. So let's have a look at an example to show this in action. So we've got 2 substituents. We're going to look at giving which one the position 1 is out of the methyl group or the chlorine. And if we go back to this rule here, we know that the chlorine has a relative atomic mass of 35.5 versus the carbon having a 12. So we're going to have this as position 1. And therefore this one, relative to that, is 2, 3, 4, position 4. So what we have here then is 1 chloro, because chlorine turns into chloro when it is a substituent. And we've got 4 methyl. And we've got benzene as the main functional group. So we have benzene as our suffix. So benzene being our suffix and our stem of the word, we know we need to put these substituents as our prefixes. just like we would with aliphatic compounds in year 1. And looking at the first letter of these two substituents, we need to work out which one is first in the alphabet. So obviously C, chloro, is first. So we're going to have our 1-chloro followed by hyphen to split any letter to any number, 4-methyl, and then our suffix benzene. So this just follows straight after the methyl. And just to remind students, because this is often a mistake, whenever you go from a number to a letter, so in all of these cases, then you need to have a hyphen in between. So you can see here, we've got hyphen there, hyphen there. Now, just for clarity, if we were to add, say, 2 methyl groups to this ring here, so if I draw this with a methyl group next door to this methyl group, this hasn't affected the numbering as chlorine is still the highest, but what it has affected is the numbering here of it being 3, 4, and then we collectively group these together and we call it dimethyl. Now we are only interested in the letter of the actual functional group, not the di-tri, which tells us the number of them. So we are still comparing C to the M. We're not comparing the C to the D here. Now, it just so happens either way that chloro would always be first, and then we would have 3,4-dimethyl, giving us this new name. Be aware, because we only need a comma, because we're not changing from numbers to letters. If we are, we need a hyphen, but because we're collectively putting those together, and then the dimethyl. So having gone through all the different rules of naming aromatic compounds, let's just see whether or not you can apply this to some different scenarios. So pause the video now and have a go. Okay, so we're going to first of all name this one. So the OH directly attached to the benzene ring means we've got a phenol. This means that the carbon that is directly attached to the OH of the phenol is designated as carbon 1. In terms of numbering, if we go this way around, we've got 2 and 3. That's going to give us our lowest combination. If we were to go this way, it would be 2, 3, 4, 5, and that would not give us the combination we want. So we're going to label that bromine as substituent 3. Bromine, when it is a substituent, is given the name bromo. So we've got 3-bromophenol. And so we've got number 3, hyphen, because we're going to a letter, bromo, and phenol. With this one here, we've got chlorine and bromine as our substituents. Now we need to work out whether or not we label this carbon as 1 or this carbon as 1. So we're going to have to look at the atomic masses of chlorine and bromine. You can see bromine is higher, so we're going to designate that as carbon 1. Therefore, chlorine is carbon 2. Now, with the halogens, if you remember, that leaves benzene as being the suffix, so it's the stem of the name. And to hand, we have 1 bromo and 2 chloro. In terms of getting them in alphabetical order, because the numbering doesn't matter here, B is obviously first on the alphabet compared to C, so it's going to be 1 bromo, and then 2 chloro, benzene. With this example here, we have some different carbon-based units. Now, in terms of numbering them, we've got 2 methyl groups here, and we've got basically a propyl group here. Which one has the higher atomic mass of the atoms that's directly attached cannot be distinguished on the first attachment because they're all carbon. But if we look at the next available atoms, you can see the methyl groups only has an option of going to hydrogens, all that have a mass of 1. Whereas this propyl group here, that carbon is actually attached to 2 hydrogens and the other one's a carbon. Now because that carbon has a higher mass of 12, then we designate this whole side group as being a higher mass. It's a bit like when you are designating EZ isomerism in alkenes. If you've got alkyl substituents, you keep going out, and whichever's the heavier alkyl substituent wins. So we're going to label this one, the propyl, as position 1. And relative to that, it doesn't matter which way round we label this. We're used to going from left to right, so we're going to label this as 3 and this as 5. Our component parts are that we have a 3,5-dimethyl, and then we have a 1-propyl. And again, benzene in this case is going to be a stem, as it is the main functional group. And if we look here, we're looking at P compared to M, which one is earlier in the alphabet. So M wins. So we're going to have 3,5-dimethyl, 1-propyl, benzene. Again, I know it's just reiterating, but we weren't comparing the D here to the P in the alphabet. We are only comparing the actual substituent name. So we're comparing the P to the M. But M is obviously earlier in the alphabet. And then this final one is actually quite important in A-level chemistry. Phenol group is 1. Then we can label any of these either 2, 3, 4, 5, 6 position. So obviously we just got our phenol part, and then we've got a 2,4,6 trichloro. So altogether we've got this name of this compound. So that concludes our video on benzene. It's introduction to the benzene and naming benzene using the IUPAC rules. If you've enjoyed this video and found it useful, ensure that you like the video, and then ensure that you subscribe to Dr. BT's Chemistry Essentials for new videos as and when they come.